So, so for today's colloquium, we are extremely happy to have Raman Sundrum. Let me tell you a little bit about Raman. So he did his PhD at Yale with Lawrence Krauss. He held postdoc positions at Berkeley, Harvard, BU, and Stanford. After that, he moved to Johns Hopkins for a faculty position. And later he moved to the University of Maryland, where he is a distinguished university professor and the director of the Maryland Center for Fundamental Physics. He, amongst his many awards and distinctions, he's an APS fellow from 2003, and he recently received the Sakurai Prize for theoretical particle physics. Amongst his contributions is the very well-known Randall Sundrum model, which he wrote together with Lisa Randall. This is a warped extra-dimensional model, which is one of the leading solutions to the Higgs hierarchy problem and almost ubiquitous now in the field of particle physics. His other contributions are in other extra-dimensional model building, in supersymmetry, in strong dynamics, in baryogenesis, in cosmic observables, and he's altogether a leading figure in particle physics and cosmology. So I want to thank Raman for agreeing to come here, and you can go ahead. So.
Okay, so let me share. Tell me when you see it. It started sharing. Okay, let me try this again. There it is.
Oh, now we can see it.
Excellent. Okay, great. Thank you to the organizers for inviting me. Great pleasure to be in Israel virtually. So I wanted to tell you about a branch of my work over the last few years that I've done with two of my students, Shobik Kumar, who is, however, now just starting as a postdoc at Berkeley, and Arushi Budas. So here's a quick outline. It is, hang on, let me get my, yeah. So I'm going to tell you about what makes particle physics like exceptional, truly unique. I want to then describe the modern paradigm, the consensus modern paradigm of cosmology, namely inflationary cosmology. I want to put these two things together and describe the sense in which the early universe can act as a kind of enormous particle collider, vastly bigger, vastly more powerful than the Large Hadron Collider. I want to show in what sense we can record the data, or the data has been recorded in the fossil evidence, and in a strange sense in which we are literally in the future going to be, if we're lucky, have a kind of time hologram. That is a kind of movie in which we can play and watch actual particles propagating at the time of the Big Bang, okay? Then all of that is not my work. I'm just telling you it. And the last 2 points are really the work I've been involved with, which is applying these ideas to exploring grand unification, gauge theories, extra dimensions, and then some basic mechanisms that allow for sort of what I'll call greater coverage. That is, this will be a desperate attempt by humans to do what seems impossible. Okay, so can we make it even more powerful? So I'm going to start with this kind of standard picture of relativistic space-time. So space is going on the horizontal direction, time is going vertically. I'm working in units of light seconds. So therefore the speed of light, or like a light ray, travels at 45 degrees in these units. And so that's just for reference in all the pictures I draw. And here are a couple of particles, two forms of matter, two particles, say. They travel slower than light, so they're always more vertical than 45 degrees. And here's a picture of two of them traveling through time and in space, and bouncing off each other due to some repulsive force, recoiling off each other. So they came together and then they drifted apart. Okay. Now, in relativity, time and space are closely related, and so they're not identical, but they're similar. And so this process of recoiling off another particle can happen not only by recoiling in space, but even recoiling in time. And that gives rise to this famous picture where you see the blue species and the purple species are recoiling off each other, but recoiling in time. And in this way, the objects, when they're traveling backward in time to recoil and then go forward in time, say, are what we call antimatter. Okay, so antimatter is, if the simplest way to picture it, is as particles going backward in time. And this process can actually happen. The recoiling in time has a kind of momentum cost. If you want to recoil, you have to have somebody give you a momentum to push you backwards. When you want to recoil in time, there's an energy cost. Energy is the time component of momentum in relativity, and the minimal cost of recoiling in this way and doing this very exotic trick is E equals mc squared, where the energy of the incoming state has to at least equal the mass of whatever new particle you're creating times the speed of light squared. Okay, so that's the meaning for us. And in this way, you can create anything you want. There literally is no qualification. In principle, you hit two ordinary things together, matter and antimatter, proton and antiproton, whatever you want. And as long as you have the energy, you can create anything you want in association with something else, but anything you want. Car, star, anything with some probability, okay? The easiest things to do are just create elementary particles, and so that's what we do. You'll notice in the picture that as you're doing the U-turn, briefly it looks like in the picture that you're going faster than the speed of light, and which is where quantum mechanics becomes essential, because quantum mechanics says that this picture is all blurred out a little bit on small distance scales. The uncertainty principle blurs out these trajectories. So as long as this U-turn takes place in this microscopic size given by Planck's constant and the mass of the particle, then it's allowed. So that's why this is a trick that requires both relativity and quantum mechanics. But in this way, we can do magic, and that's what we do. Okay, so the CERN Large Hadron Collider, or it would have been more obvious if they just called it a Large Proton Collider, which is what it is. Here is a picture of it under the Franco-Swiss border with these racetracks for speeding protons and then colliding them. And the protons contain a lot of gluons, which are their own antiparticles. Okay, and so they're colliding, and then they can make very exotic elementary particles like a top quark and an anti-top quark. And the cost in energy for doing that kind of magic is the mass of the top quark, which is 175 GeV. The proton collisions taking place have a much bigger budget of 14 TeV, but it's not an efficient process, and we only get to keep some of the particles in the proton and so on. So we can do magic like this, and we can study new elementary particles. And this is a grand process. Just to bring you up to date, this kind of bouncing back and forth in time, or playing with matter and antimatter, is the kind of process that at second order can sort of lead to creating a Higgs boson with this E equals mc squared. The Higgs boson is a central player in the unification of electromagnetism and the weak nuclear force. Here's a picture in the detector of a Higgs candidate event from its discovery in 2012, the CMS detector. But particle physics in the laboratory, in the Large Hadron Collider and other labs, are trying to do a number of exciting things. There's this major discovery. They are at the moment trying to recreate, using E equals mc squared, they're trying to recreate dark matter particles. They are trying to find out what particle physics is responsible for the fact that there's more matter than antimatter in the universe. They are trying to find superparticles associated with what I sometimes call fermionic extra dimensions, okay, or supersymmetry. I think somebody may have had a Yes, that's right. Somebody, I noticed this through the corner of my eye, that somebody is, Erez, is pointing out to me that the LHC also collides heavy ions, which is why they had to use the generic term hadron. My apologies. Okay, so for our purposes, it's a large proton collider. Okay, so particle physics is going on in this laboratory conditions. It's very exciting. The goals are truly, fantastic goals. I hope you'll agree. Here is sort of, I used to read a lot of ancient mythology when I was a kid. I never actually read any physics or cared for physics. And in ancient mythology, all the gods were actually forces of nature. And they were all related to each other. They had a family tree. And little did I know that, in fact, that's true, that here are all the forces of nature. And as from the Big Bang on, they've been giving birth one to the other, bifurcating, having children, dying in the process, et cetera, et cetera. And so here's just a quick sign. In the colors are more, the evidence for this is more solid. The black lines, there may be dark sectors that we haven't seen yet. But this is basically a picture of what we think is going on at super high energies. You can create black holes. Energy you can run this way in a logarithmic scale. There's kind of a Planck scale at which particle physics switches over to black hole physics. But basically from this fundamental god of quantum geometry has come out all of these things. Now, do we know this for a fact? You see, this to me is a kind of map of particle physics, which I had to show you. But it is a map, not in the modern sense of a map. It is an ancient map, like the maps from 1,000 years ago or 2,000 years ago. We actually have only explored with our colliders up to sort of this level, and we haven't even been able to really see very much in the dark, but we're all just probed up to here. So the rest of this map is coming from indirect evidence, from some guesses and hopes and some aesthetics and so on. So this map is an explorer's map. We don't know if it's completely true. We suspect something like this is true. So I'm showing you this because it represents our grand ambitions. The LHC can probe up to this scale so far. Gravitational wave detectors, well, let me explain something. The bifurcations where the gods give birth, okay? These, from the particle physics point of view, we would call these Higgs mechanisms. Like this one has been studied by the LHC, okay? If you run it in cosmological time, you would say that these bifurcations are kind of phase transitions in the universe, which can lead to gravitational waves, stochastic gravitational waves, which can be picked up by gravitational wave detectors. Okay, so that's another branch of exploration. I know that Alessandra Bonanno, my colleague, is showing up in a couple of weeks there, maybe talking mostly about astrophysical sources, but there's also cosmological sources for gravitational waves. What I'm talking about today is something vastly more powerful than the LHC by maybe 10 orders of magnitude, called cosmological collider physics, okay? So onto that. Here is a picture of the expanding universe in my space-time sense. So these two dimensions, the horizontal dimensions here represent three-dimensional space. Here are the galaxies, and it seems like all of them are getting further away from us. Of course, you all know that it's not that we are special in this regard. Rather, the entire sheet, three-dimensional sheet, is being stretched in the general relativistic description. Space-time is getting stretched so that tomorrow the galaxies will be further apart, or the galaxy clusters will be further apart. But if we run in reverse, which is really what I want to do, then the densities increase, because if you run in reverse, then space-time is contracting, space is contracting. And ultimately, the densities get so high, the temperatures get so high, that all you have is a very vanilla cosmic soup of elementary particles, where the densities are much higher than the densities today. And if you keep trying to use general relativistic theory to run the movie further back, then at a very finite time, which you can call the Big Bang, the density becomes infinite, okay? So there's a kind of mathematical singularity in which we know nothing. However, this singularity can be avoided, or at least delayed backward in time, which I really mean preponed. It can be made earlier. I can push this singularity earlier. If we could get rid of all the matter and radiation in the universe when we are running the movie backwards. It's the matter and radiation which are gravitationally back reacting and creating this Big Bang. If we could just somehow get rid of it early in time, then we could avoid this catastrophe. Now, you might say, who needs to avoid it? And I won't give you all the reasons for wanting to push time further back. But I'll give you one of the most important ones later on. Okay, but let's just try it. What does it mean to say I get rid of the matter? Well, it means this picture. It means that all the matter and radiation was not eternally there. It was created at some time, we'll call it the reheating time. It was created by some sort of E equals mc squared miracle, just like I showed you in the lab. In some way, we're going to create the particles. And therefore, they're sort of bending backward and forward in time in this way. And if they are created at this time, then we can avoid, as we run the movie backwards, hitting this Big Bang singularity. Okay, so we can talk about it before the creation in that sense. Okay, but the question is, who is this E equals mc squared? In what I showed you, the only E equals mc squared source were some pre-existing particles, which defeats the purpose in this case. We need some other source of energy, which is not these sort of pre-existing particles. And so here's the quick picture. Here's the analogy. There are sort of two different forms of energy in this picture. This is just an inclined plane where the ground then suddenly drops. Okay, so then suddenly you're on the cliff's edge in some way. And as the ball slowly rolls, it mostly, in this region, it mostly just has potential energy. It's not what we normally in English would say was energy. Energy means motion, right? So it's potential energy. So it's like a little battery, and then at some point it gets released, and then suddenly it becomes our real image of energy, something fast, and the energy is released. So of course, we know ways in which you can store energy and then release it at some given time. In this picture, I'm moving in space, and this potential energy is created by the Earth's gravitational field because I have this terrain. Okay. Well, I'm trying to apply that principle to cosmology. So we're not living on Earth with the gravity pulling down, right? So in this picture, the horizontal direction is some other quantity. It's not x, okay? It's not space, it's some other quantity. Let's call it phi. But it has some potential landscape. And the phi quantity is moving as a function of time in exactly the same way, with a little friction and rolling slowly, and then suddenly picks up. And then this energy is released in phi, and it's the E equals mc squared that is needed at that moment to create all the particles and radiation that we now know. Now, you can think of it, therefore, as this phi as a function of time. The motion of this quantity phi is like the alarm clock of the universe. While it is slowly moving and there's no particles and no matter, the universe is asleep. And then suddenly the alarm clock goes off and reheats the universe, creates all the particles and matter through E equals mc squared, and suddenly the universe is awake. Okay. Now this phi is a function of time. That's clear. But in relativity, time and space always have to go together. So it can't just be a function of time. It has to be a function of space and time. In that sense, you should think of it not as a single clock, but an array of clocks, one clock at every place in space. And the clocks in my story, the clocks are approximately synchronized. Okay. So this is the picture of the approximation of the synchronized clocks. Now, this potential energy gravitates. All forms of energy gravitate. They gravitate in different ways. Potential energy, when combined with general relativity, gravitates in the following way. It gravitates by giving you exponential expansion of space So the usual Pythagoras theorem for distance is multiplied by this exponential function of time. And this is the famous, approximately true, which is good enough for my talk. It's basically de Sitter space-time. Okay, that's the name of the space-time. And this parameter, the exponent for exponential expansion, the Hubble parameter during inflation, is related to the potential energy of this plateau, when you're potential dominated, and G Newton and C squared. Okay, so it's given in some way. Because of this role in exponential expansion of space-time is called inflation, and therefore the field that is responsible for inflating and then stopping inflating by dropping down and reheating the universe is called the inflaton field. Okay, so those are the names. So the picture looks like this now. There is the inflationary era where the ball is at the top of the hill and slowly rolling, or the inflaton is at the top of its potential and just slowly coasting along. And then later, when it suddenly realizes its full potential energy as kinetic energy, that is by coupling to matter and radiation, it allows the E equals mc squared process to suddenly take place. And we create the modern universe, shall we say, okay? But I wanted, a crucial role is played by quantum mechanics here, okay? So it's the extra thing that this Hubble's parameter is a form of energy, okay? In the units that I'm using, it's like this, okay? It's roughly corresponds to an energy scale, and it allows you to have a more modest kind of quantum. This is in some sense a little small, and it allows you to have a modest amount of quantum creation through the magic of E equals mc squared. But it's all taking place in this exponentially expanding universe. So the process of quantum creation is create something, expand and dilute whatever pattern you create, then create some more through quantum creation, and then expand and dilute a little more, and repeat and repeat and repeat. And the creation is, of course, quantum mechanical. It has some random aspect to it, but averages are predictable. So, but this process then creates a random fractal of some sort, okay? Which is, what I mean is, it's on the spatial side, it is self-similar. Different length scales look self-similar. The technical term we use in cosmology is we just say it's scale invariant, okay? So we're expecting that, and I'll show you a picture of what that looks like in a minute, okay? So this is exciting, that quantum mechanics is coming in to change the story a little bit. And we can picture it here. This is the expansion of space taking place, which is this Hubble parameter. And we are creating, in particular, we are creating inflatons. We are creating the quanta of the inflaton field. Okay, just like photons are the quanta of the electromagnetic field, we create them, and these sort of trace amounts of inflatons go and they perturb. Since the inflaton, basically what's happening is you had a synchronized set of clocks, but quantum processes are desynchronizing them or asynchronizing them by small amounts. So the clock here is not exactly on the same as the clock here. So the universe reheats at different times in different places, which means that this, what looks in the picture like a surface, is rippled. Okay, it's not homogeneous. It's not uniform. Now that is a wonderful process for us, because in a sense, these sort of trace amounts of particle creation, like these inflaton particles, they are detected by the reheating surface, in the sense that they are, the hits from these inflatons are desynchronizing the reheating surface. And the reheating surface is a bit like kind of the start of a photomultiplier detector, okay, in the sense that there are trace amounts of particle creation here, and they're being expanded onto very large length scales by inflation. And then when they change the reheating surface, they modify, they make non-uniform the enormous amount of particle creation basically a universe worth of particle creation and that takes place at the reheating time, which is sort of like the electrons in the photomultiplier tube. There's an avalanche that takes place after that, but the avalanche is being made non-uniform in space by the instructions of these quantum particles. So we can think of this as like our quantum lab during inflation, and the detector is everything that happens. But how do we detect what happened back here? Well, these non-uniformities, we literally are these non-uniformities, okay? These quantum mechanical non-uniformities evolve through gravitational effects, Newton's law, etc. They form galaxies. There is more matter here than here, and we are part of that. So basically, the matter density today is a record, a processed record of this ancient events, okay? This kind of process. And so is the cosmic microwave background, which is the light coming to us from the last moment where the universe was opaque to light. So this is the instant at which the universe became transparent to light, as the universe cooled and neutralized its atoms. And so we get light from the sphere coming to our eye, traveling at 45 degrees. So let's take a look at these two pictures to see if they fit this kind of story I'm telling. So here is, for example, the cosmic microwave background. If you just look with your eye, the non-uniformities are very, very small. To be even visible, you have to exaggerate this picture by 100,000. So here's the famous map of the sky taken by the Planck satellite. And indeed, if you just look at it, you'd say, yeah, that could be a random fractal. That could exactly be what's coming out of this. Now, if you study it in greater detail, you find, as you study it on length scales at the radius of the sphere I just showed you, or if you want on angular scales, you find that there's structure, but we understand the structure. This is structure that was in the map. This is structure that was created after the reheating surface, okay, by processes of the standard model, which by and large we understand. However, if you rewind the movie, if you rewind this map back to the reheating surface, you find that indeed it looks statistically scale invariant. It's like a random fractal created by this kind of process that I just showed you. Okay, and we can study the statistics mathematically. We can study it by looking at 2-point correlators of the temperature of the CMB here and the temperature of the CMB over here in these temperature correlators. And the 2 points, if you want, intuitively, these 2 points in the sky correspond to where, say, they're creating this correlation due to the inflaton basically being created, and then each inflaton sort of traveling and making a hit on the reheating surface. Okay, and in this way, we can basically use a fit to the cosmic microwave background, and the data tells us that the Hubble scale of inflation is only constrained to be smaller than 5 × 10⁻13 GeV. So it could be as large as this scale, which would be an energy scale 10 orders of magnitude bigger than the energy scale of the LHC, okay? And we are in a kind of quantum lab in which particles are being created in a process analogous to the LHC. So if we can record this data then and see what's going on, analyze it, we are in business. We have this enormous collider, okay? Here also, for the record, is sort of looking at galactic structure on the largest scales of the universe, the observable universe. And again, the 2-point correlators in the density also, if you rewind the movie back to the reheating time, also fit the idea that the hypothesis of inflation, that you have a scale invariant distribution of non-uniformities at that time. Okay, so again, a kind of random fractal. So I just want to at least pause and say there's something strange about this. You see the fossil evidence. It's kind of a static picture of the universe, like the CMB. It's a static picture of the universe at some moment in time in cosmic history. So it doesn't explicitly know about time. It's like a fossil. It's just not changing. but the image of time can come about in a funny way. I just want to show the cartoon and then we'll do the math. Okay, so the cartoon is this. Here is, here is a picture of me when I was a baby, and I'm talking about the picture, okay, the images of the photons. And imagine that the images are getting, since it was taken long ago, the picture is getting stretched by inflation. So when you finally see this picture at some fossil time, reheating time, it looks big. And here I am as a little boy. I'm still wearing the same shorts, but at this time, it's later, but on the other hand, I look slightly more mature. And then here I am today. It's much later, and the universe hasn't had as much time to stretch out my image. So all of these things are splattered on the recording device. The recording device is the reheating surface, okay? And now this thing is happening all the time. Little Ramans are being born, going to school, giving colloquia, and so on. And it's all getting splattered on the reheating surface. So it's a nightmare, it's a mess, okay? It's just fractal noise. How am I supposed to see any of this? How am I supposed to decode? But it's fascinating that time, the movement in time, is somehow going to be imprinted on a static thing. We are literally being given the videotape. Okay, so before we talk about that, let's do something simpler than Raman's life. Here is a particle being created. Let's say a particle with mc squared comparable to the energy budget for creating particles. The expansion of the universe is creating this particle, particle and antiparticle. And then let's say this particle and antiparticle decay into inflatons. Inflatons are those particles that have the strongest effect on rippling the reheating surface. So they're very efficient for being detected. So imagine that we can create these particles. These particles would be created, and then they decay at various points into the inflaton, okay? So that means that now we would say that the image of this should somehow show up in our fossil data. They should show up, but now they should show up in what are called non-Gaussian correlators. That is, non-2-point correlators. In this case, a 4-point correlator like this. Say, galaxy surveys should show that there is some information in these 4-point correlations, or so-called non-Gaussian correlations. And it should somehow represent this. It has to somehow know about this. We can make it slightly easier by going to 3-point correlators, where this fourth line, you can think of it as a kind of stimulated emission, because there is a background classical process that I showed you at the beginning of the rolling phi field as a classical field. And in that sense, it contains a lot of bosons made of the inflaton, just like an electromagnetic field contains a lot of bosons made of photons. So we can turn this, it's a minor point, but we can turn it into a 3-point correlator, which is just technically easier, okay? So we want to know, what is it about this 3-point correlator that we should do to recover the movie, and I really mean movie, of what happened back then. So here is the little bit of math. Obviously, we're talking about length scales and the expansion of the universe, and we have translational symmetry fundamentally. So, okay, do the Fourier transform of the 3-point correlator. That gives you this function f. This delta function is just keeping track of momentum conservation, because these wave numbers, k1, k2, k3, multiplied by h bar, are basically the momenta of the inflatons that you're finally decaying into. So just reflecting the fact that momentum is at least conserved, spatial momentum is conserved. There's a delta function like this, so you can pick in momentum space, you can just picture it as a triangle that enforces the momentum conservation. So the non-Gaussianity is fundamentally a function of triangles in momentum space. In fact, at the approximation that we have scale invariance, right? That we still have scale invariance, the random fractal. It doesn't even care about the scale of this triangle. It only cares about the shape. So it's a very beautiful thing that the data that we are talking about is a function of shapes of triangles, okay? And if you just want, you know, a whole function is a lot of information. Often when people are trying to quickly exchange estimates, they ask, what's the going rate for this non-Gaussianity F? And they call it little f and L for historical reasons. And they just say, well, let's just estimate the entire function by its equilateral point. And that's sort of the going rate. But of course, we want the entire function ultimately. Okay, so that leads to this subject of cosmological collider physics, which basically says, if somebody gives you the 3-point function, how should I read out the movie of the quantum events that imprinted to give that 3-point function? So we go with this basic fact that we have exponential expansion of space-time, and what is it of space during inflation? And what it says is that these wave numbers, K1 and K3, are basically the time at which you decay into one pair of particles, K1 and K2. Sorry, when the heavy particle that you created decays into a pair of inflatons with momentum K1 and K2, and the other pair decays into an inflaton with K3, and the other sort of joins the classical background with K equals 0. So if we imagine that K1 and K2 are big and K3 is small, then this K1 and K2 is a late time decay. So we have a late time decay, and late times or large K means that the sort of this correlation is that the late times are proportional, you know, small wavelength or large wave number is proportional to e to the h times late times, and small momenta are large wavelengths which have had a lot of time to expand in the inflationary universe, so they're proportional to the early time. And so basically this is telling us this fact that K1 over K3 is e to the Hubble times the time difference in the two decays of the heavy particle. So in this way, one can calculate the non-Gaussianity as a function of triangles in momentum space. And I want to break this down bit by bit for you, but basically there are two significant factors. One is this factor here, which I'll explain a little more later. It's basically saying that if the mass of the particle you're trying to create is much bigger than Hubble, the energy budget for creation, then you don't create. You basically highly suppressed. But otherwise, if you just look at the function here, you would say it should somehow be sensitive to the propagation of the heavy particle. So as you know, in quantum mechanics, particles propagate by Schrodinger's equation by e to the I energy times time divided by h bar, right? That's the classic Schrodinger equation solution. Here, the E is sort of the mc squared of the heavy particle. Okay, so that's this factor here. We're propagating between two times, early and late, so that's the delta t. And this e to the delta t, well, we have this formula. Okay, so we can just plug this in for delta t, and we find this result. Okay, so I'll talk more about exactly how to think about this later, but basically we have two intuitive features. This is what I've explained basically here and from Schrodinger's equation. This is basically saying that if the mass of the particle is much bigger than Hubble, you can't afford it. It's outside your energy budget. So what we see is this factor. If you give me this function, which is a function only of space, which is Fourier transformed. If you look at this fossil record of, say, galaxies, the galaxy map today, right? If you look at it and you look at the non-Gaussian features, then you can probe it on different values of k. You can ask, what are you as a function of this triangle? What are you as a function of this triangle? And when you put it together like this, you are actually getting, when you look at the proportionality factor, What you're actually recording is the movie of the particle propagating. Okay, some particle that may long be dead is propagating in this way. Okay, now it's important to say that there's a window in which you have observability. If the mass is much smaller than Hubble, then this factor could be called approximately 0, and you lose this characteristic way of diagnosing. So you don't want the mass to be much smaller than Hubble. If the mass is much bigger than Hubble, you can't afford it in the energy budget created by Hubble expansion as an energy. So you want masses which are comparable to Hubble. That's the window of opportunity. And then you can hopefully see something, okay? To date, we have not seen anything yet. That's because this is a game of extreme precision. You see, we can only calculate theoretically quantum expectations. And we only have one universe. So you can ask, what good is it to calculate a quantum expectation value when the only experiment is one universe in which to do any measurements? However, if you look at these triangles that we're really measuring functions of these triangles in momentum space, we can get equivalent triangles. It doesn't care about the orientation. We can rotate this triangle spatially and get the same physics, because physics is rotationally invariant. And we can rescale this triangle approximately because the universe at that time, inflation, is scale invariant. So in that way, we can make many equivalent measurements, even though we only have one universe in which to do one experiment. But we can effectively get many measurements. And hopefully, if we can get many measurements, they will correspond to the quantum expectation value that the theorist can calculate. So the question is to count how many different ways can I move these triangles around and so on. And I'll give a very sloppy estimate that the statistical error in the measurement of non-Gaussianity is of order 10 to the 4th times the square root of the number of kind of modes, these momentum modes that we have to count. And different experiments have different number of modes that they can measure. So here is my single experimental slide. It's worth another colloquium by a real, cosmologist. This is distance away from Earth, which is to say, measured in terms of the redshift z. Okay, so there is a body of data which is coming from looking at galaxy surveys, the kind that is going to get radically improved in the coming decade. In the next few years, we're going to get a radical improvement in this data set. It's coming mostly from low redshift, from the universe closer to us, where galaxies would have even formed by that time, by the time light reaches us. The Planck satellite, for example, the cosmic microwave background, comes from a very early time, very, very far away. It took light a long time to get to us. And you can see it's essentially a two-dimensional map, because in the radial direction from Earth, it is almost a delta function in this picture. And so you get a two-dimensional map. It actually gives us our best constraints on non-Gaussianity today, that this delta FNL is of order 10. And it's kind of maxed out. We've pretty much exploited everything we can to see that we have not seen non-Gaussianity of the type that I'm saying is so exciting with these 10 to the 7 modes of the CMB. But this is all about to change, because we're now about to get 2 order of magnitude improvement, which is an order of magnitude improvement in our sensitivity to non-Gaussianity coming from these various types of galactic surveys. And the ultimate, just to keep your eye on it if you're young, is 21 centimeter cosmology, which would look at this enormous region of depth into space using 21 centimeter cosmology in the so-called, it's one of the dark ages of the universe, where you'd get 10 to the 16 modes. That's an enormous improvement over here, where the ultimate precision on non-Gaussianity that I want you to keep in mind is of this 10 to the minus 4, 10 to the minus 3 level. The trouble is you have to be pretty young to, or just live a long time in order to see it. But it's an exciting direction. It might require putting instruments on the backside of the moon. It'll be great. and I assume it'll get done. So I want to just apply it. As I said, most of my talk was just setting that up. Let me give you an application from my own work. What's worth seeing? What could be up there in energy scale, 10 orders of magnitude above the LHC that's worth seeing? So one example, just as an example, is grand unification. Okay, truly exciting idea. I'm doing the simplest form of grand unification. So as you know, electric charge has subtler analogs. In the weak nuclear force, we have charges called up and down, or isospins for the weak nuclear force. In the strong nuclear force, or quantum chromodynamics, we have quark colors, sort of called red, green, and blue. And these are different types of charges because they are group theoretically subtler structures than just ordinary electric charge, which is plus or minus. These have a group theoretic structure, which is described by gauge theory. Okay, all the laws that we know have that gauge theoretic form. But if you look at the indirect evidence we have here, you find that all the charge assignments are strange assignments until you consider the possibility that they all were inherited from a mother force, a grand unified force, which is simple, and then its children look like they have strange related features. Okay, so and then the other one that I'll just actually show you the data for is, if we look at the coupling constants associated with the three forces, and I'm oversimplifying a slight bit, but if you look at the coupling constants and we plot it as a function of energy, because these coupling constants are actually not constant. Quantum effects make them run as a function of energy. So if you go to very high energy scales, you find them all coming together almost in a very striking way that suggests that they all were once upon a time at very high energies or very early times in the universe, part of the same mother force, the unified force. Okay. Now, if you look at where they're coming together, it's sort of similar to the scale, the maximal scales of the simplest theories of inflation. The simplest theories of inflation have Hubble parameters that live in this ballpark. Great, perfect coincidence. Let's look for it. Okay. So the simplest theory of grand unification has this very simple extra dimensional form. So here is an extra dimensional interval, and three-dimensional space I'm just drawing as these vertical planes. Okay. And the simple theory, I'm oversimplifying as usual, is that in the bulk, in this four-dimensional space here between the edges of the interval, is a higher dimensional unified gauge theory. By unified, I mean all force fields are interchangeable. There's no way to say that this is more special than this. They're all symmetrically interchangeable. And of course, wherever there's space, there's gravity. Okay. But this interval is really microscopically small. How small, we'll figure out in a second. It's microscopically small, so that on long wavelengths, which is mostly the way you live your life, it's so small that this is you sandwiched in this tiny interval. And of course, you have no idea that there's any extra dimension. It's microscopically small, and you don't even see unification with your eyes. It looks like there are three forces of nature on this scale. But if you really want to see unification, you have to access wavelengths which are smaller than the size capital L. Okay. And of course, at the quantum level, if you want to see with a photon, you have to pay the quantum price of a photon, which is Planck's constant speed of light over the wavelength of the photon, as is famously familiar. So that means you need energies to see inside the extra dimension. You need energies bigger than this scale here. And this is the scale at which unification becomes apparent. And as you saw when I showed the running of gauge of the couplings of the standard model, they all unified around somewhere in the ballpark of 10 to the 13 GeV. Okay, so this is how we should identify the size of the extra dimension. And we basically want to get to that kind of scale, but we need this kind of wavelength that is comparable to this. Now, these wavelengths are waves in a box. In the extra dimension, you're doing wave physics in a box. Famously, waves in a box are discretized in their wavelengths. And so this energy that you're going to need is quantized in units of this scale. Okay, so you're going to have integer times some sort of going rate scale, right? This minimum quantum of energy. And these discrete energies of these discrete waves are called Kaluza-Klein excitations, okay, for a photon of this. It's a Kaluza-Klein excitation. In fact, sorry, let me go back just here. What we're talking about, the easiest thing to shoot for is not a photon. Something even more exotic would be a graviton. One quantum of the gravitational field in this extra dimension, a Kaluza-Klein graviton. So that's what I've worked out here as my example. So here is a picture of the going rate of non-Gaussianity. Remember, 10 to the minus 4 is like the statistical error that is absolutely fundamental in this game. And you can see that as a function of the mass of the or the energy of the Kaluza-Klein graviton in units of the Hubble scale, as long as it's comparable to 1, then there's a rapidly falling but observable signal. Okay, it's not all cartoons. You can actually work out the form. That's the pain in the neck. You have to actually do calculations, so you can work out the formula for what the non-Gaussianity is. The only thing I'm going to point you to, of course, there's this factor here that I talked about earlier, so that's not surprising, is because the graviton is the only possible spin 2 elementary particle. That's a theoretical statement from quantum field theory. It's the only possible elementary spin 2 particle. So it would be great to see the spin 2 nature of the graviton imprinted so we know who is propagating. Who are you that's propagating? Well, it's given by this kind of angular dependence where the angle theta is this angle in the triangle in momentum space. Okay. Very good. So I just want to take 2 minutes, if I can, just literally to say everything else. I just wanted to give some example there. Among my other work, the question is, this exponential suppression when the mass is large compared to Hubble is analogous to a Boltzmann weight in statistical mechanics. And that's because rather than thinking of the Hubble scale as a sharp energy, it would be better to think of it as a temperature of order Hubble, where it's famously the temperature is the Hawking temperature of de Sitter space-time. It's not the Hawking temperature of a black hole, it's the Hawking temperature of an entire expanding universe, and it's basically given by the Hubble scale. So that this kind of factor is very much like just saying you're Boltzmann suppressed. If the energy, mc squared, gets much bigger than the temperature, then of course you're suppressed. Okay, so for very heavy particles, if you wanted to go even above the Hubble scale, your ambitions know no limits, then you would have very few particles because their energy E equals mc squared is Boltzmann suppressed. Of course, in thermodynamics, if you have very small particle number, you can always bias things by introducing a chemical potential. Okay, effectively, instead of the energy being mc squared, you can add a chemical potential term, and you can, oddly enough, you can do the same in cosmological collider physics, where this chemical potential is coupling the heavy particle directly to this background inflationary trajectory, which, even though it is moving the kinetic energy of the ball on the inclined plane, it's small compared to the potential energy, but it can be much bigger than the Hubble scale. Okay, and I'll just say my own contributions to this with my students is just that we've generalized this beyond the original things into something very robust and powerful. And I won't specify in what way, but I did want to show a picture because I wanted to show what does it mean when you say I am seeing a particle propagate that existed before the Big Bang. What could that possibly mean in the data? It means here is the non-Gaussianity. Here you're probing it, you Fourier transformed it, you're probing it on as you vary the shape of the triangle, and you're literally seeing these waves. That's what I mean by see. I mean, it's videotaped in this sense. And with this chemical potential trick, we're actually, as I'm showing these two colors, able to probe masses considerably beyond the Hubble scale. Okay. We're talking about, in this way, being able to probe like this 40 Hubble, we're talking about being able to probe energies up to 10 to the 15 GeV. It's getting very close to this Planck scale, the ultimate scale in particle physics, where you switch over from particle physics to black holes. It's incredible. It's mind-boggling. Okay. Similarly, there are other variations I have no time to talk about, that even these prefactors that I didn't talk about can be made bigger than they are. What's important is they can be made big enough that many exciting signals could have non-Gaussianities that could be probed in this decade by galaxy surveys. Finally, I'll just say most of my work was actually just studying the structure of gauge theories with cosmological collider physics, which was in its infancy, shall I say, when we started our work. In particular, gauge theory says you need charge conservation, whereas the inflaton is neutral. So the kind of picture I've been drawing, where you create a charge particle and it decays, would violate charge conservation. And yet this is the dominant diagram over things like this. But my work with Shobhit Kumar was basically to say that when you have a Higgs mechanism, which, if you like, is a Bose-Einstein condensate of charged particles, then effectively you can violate charge conservation by borrowing charge from the Bose-Einstein condensate, which is masquerading as empty space. Okay, and in this way, one can get interesting gauge theory non-Gaussianities of order 1, which are within striking distance of galaxy surveys this decade. Last point, and then I'll stop. All observed elementary particles in the standard model, basically, all observed particles have masses which are proportional to the strength of the Higgs Bose-Einstein condensate times couplings, the couplings that these charged particles have to the Higgs boson. And in this way, we understand mass in the standard model. The particles we've seen have masses which are secretly a kind of reaction to traveling through a Bose-Einstein condensate. If the condensate wasn't there, all the particles we've seen to date would be massless. But in this way, they get masses of order 200 GeV or less. This is much smaller than the likely energy scale of inflation. And as a result, they would be outside the window of opportunity. Okay. However, famously, the standard model Bose-Einstein condensate is highly unstable. So another part of my work with Shobhit Kumar was to show that space-time curvature effects, coupling the Higgs to general relativity, has a very simple coupling that naturally takes this 200 GeV scale of the Bose-Einstein condensate we see today and makes it comparable to the scale of inflation, the Hubble scale of inflation, during inflation. This Hubble scale of inflation is a form of space-time curvature. And when it couples to the Higgs condensate, it drags the Higgs condensate up to that scale. In this way, all of the elementary particles that we see at low energies today, like the W, the Z, the Higgs boson, the top quark, they would all have masses in the window of opportunity. This is a mechanism we call heavy lifting. And yet their mass ratios would be unaffected or affected only by small amounts that we can calculate. Okay, so that's the last sort of trick of my research. Okay, I've gone way over, and I'll just splat on my conclusions. They're almost readable yourself. This is a huge, I think the only thing I want to confess, I'm telling you things which are hugely ambitious, clearly. But I have to confess, it does require some luck for the parameters in nature to be such that the amazing potential is fully realized in these primordial correlations. Okay, that requires luck. we are still working out new mechanisms and models for what might show up. There's an enormous amount to do to realize this ambition. It really is something for the future of cosmology. Of course, the experiments are hugely ambitious. You need to assess and subtract any kind of backgrounds. They're really foregrounds from astrophysics. In the late universe, you need to be able to calculate a lot of the late universe processing so that you can wind the clock back in the fossil record back to the reheating time. And ultimately, you need to develop signal templates based on these formulas that I'm showing you. All of that remains to be done, but I'll stop there. Thank you.
Thanks, thanks, Raman. Any questions? I see some people raise their hand. So Ido, go ahead.
Yeah, so I was wondering this chemical potential. So is it robust to different models of inflation? I mean, how robust is this, let's say, for single field inflation?
Yeah, so it is in single field inflation, which for those who don't know is maybe the minimal kind of inflation. It's actually quite robust. In fact, our contribution to this was to really point out a version which is very robust. And also has a very high reach. It changes Hubble energy scales that you can access to, 60 times that. It is actually very robust, but it does have a key feature that I didn't have time to say. It has to couple the inflaton not to a single heavy particle, but to pairs of heavy particles. Or if you want complex fields, okay, not real fields, but complex fields. That's because you need to have some sort of notion, just like any chemical potential, you're coupling to something that has a kind of charge. Now, the heat bath might violate that charge, but at least the charge should be defined. So the only key thing is that this trick requires that you have some notion of a charged particle that you're creating. So just as an example where it doesn't work, because you're saying, is it infinitely robust? No. The Kaluza-Klein graviton case that I just studied earlier, that graviton is a real field. It doesn't carry a charge. There are other versions of extra dimensions in which gravitons do carry charges, but the one I showed you doesn't carry a charge, so this mechanism would not apply in that case. And it didn't need to in that case, but it couldn't have. But it is quite robust, even in single field inflation.
Okay, yeah, go ahead.
Thanks for the really nice talk, Raman. So the scale of 10 to the 15 GeV that you're getting is, of course, very close to the seesaw scale. So do you think we'd get information about neutrino masses and right-handed neutrinos this way?
Yes, in fact, in my desperate attempt to show off and only talk about myself and only refer to people in passing, I should say that the first idea, this first paper here, was actually describing the chemical potential approach applied to neutrinos. And so it was applied to neutrinos. It could give information about right-handed neutrinos. That is absolutely a possibility. The reach, in this case, the neutrino story that they wrote was, it had a smaller reach than the 10 to the 15 GeV, but we don't know exactly some order one number. So in answer to your question, absolutely. That allows me to make a very important point that I think is obvious. None of the things you see come with name tags saying, I'm the right-handed neutrino. But they can come with information. I showed you angular dependence can tell you about the spin of the particle, the mass of the particle. We can read off from the dependence on wave numbers. So there's a lot of detective work that's, if you see something, just figure out, oh, that's the right-handed neutrino, or that's, you know, the Higgs triplet of unification, the color triplet of unification. You're going to need other information, and that's why I call this is a desperate, ambitious gamble. Not just to see something, that's what I said in my conclusion. It's not just good enough to see something, but to interpret it. Of course, if you see something, come on, somebody's getting a Nobel Prize. But it would also be good to interpret it. That's why when I wanted to show off, I did the Kaluza-Klein graviton, because it was uniquely the elementary particle with spin 2. So I showed you that one, because it does come with a name tag. But I want to confess at this point after the talk, you know, things, it's a tight game, but it could see neutrinos, heavy neutrinos.
Thanks.
So I also had a question.
Yes.
So first of all, you're here focused on the case where Hubble is at the highest
Yes.
of its possibilities. But what about, can you say something interesting also about, let's say, when Hubble is for the TV or something like that, where you could see maybe known dynamics, but from cosmological collider physics?
Yes. So most of what I have talked about has in other words, the basic grammar of cosmological collider physics that I discussed is not dependent on whether Hubble is the maximum it could be at 10 to the 13 GeV, or whether it is, you know, 10 GeV. Okay. Wherever it is, it gives a window of observability. So in a sense, your question makes perfect sense. Why did I focus so much on the highest scales? Well, one, I am by nature a particle physicist, and therefore I come with a terrible prejudice that higher energy is better. Of course, that's not always the case. Two, I wanted to show off something with a name tag, spin 2. And for the graviton, the closer you are to the Planck scale in Hubble, the bigger the signal. So I wanted to show that off, and so I did. Three, in some of these things, like suppose you saw this heavy lifting mechanism that I was talking about here, where suppose you see the mass and spin of all of these particles, but rescaled by a factor of 10 to the 10, okay? Then they might come with name tags because their mass ratios are not changed, okay? Their mass ratios are unchanged, and we know their mass ratios, and their spins are unchanged, and we know their spins. So that would be shocking, okay? However, the saying that the mass ratios are not changed is actually only an approximation. They would change because the masses are proportional to these. This is what's changing during inflation. These are coupling constants, but as you know, coupling constants secretly they run slowly. So these mass ratios, if you can measure precisely enough, these mass ratios would run according to the renormalization group, which humans know how to calculate. But in order to calculate it, you'd have to say, well, how far should I run in energy, right? It would be good to know what is the scale of inflation. And as you know, the so-called tensor to scalar ratio, which is an observable and a target of the next stage of cosmological measurements of the CMB, if you have high scale inflation, then measuring the ratio of gravitational waves, or the polarized CMB, to the scalar perturbations will actually give you the value of the Hubble scale. And then you'll even be able to do something like this, where you run the couplings up to that scale and look at mass ratios and see whether that's what's going on. If you talk about low scale inflation, the scalar to mass, the tensor to scalar ratio that allows you to identify the scale goes blind, effectively. And so you don't know what the scale is. So you may see some interesting signals, but you won't even know what the E equals mc squared of those particles is. Still, it would be exciting to see something. So the quick answer to your question is, yes, most of what I say is true for low scale inflation. But some of our best experimental handles get harder. And I'll say one more thing. I've played with trying to build models of low scale inflation. It is hard to do. Since I think that theorists are smart, and I think I'm smart, I'm getting the impression that if I were a gambler, I would gamble on high scale inflation, and that low scale inflation is just harder. Not impossible, but harder. So I don't put much, I haven't put as much emphasis on it myself.
Okay, thank you. Any other questions for Raman? Okay, so if not, let's thank Raman again.
Thank you.
Thank you very much for coming. It was a real pleasure. I guess see you at some point.
Absolutely. I'll see you at Zoom lunch sometime.
Yeah, and also hopefully you might come when it's possible.
That's true. Yes. Great. Thank you very much.
Thanks a lot, Raman.
Bye.
Bye.
Bye. Take care.
See you, Erez.